All right. Hello, everyone. Um, Professor Boyd needs no introduction. So instead of telling you about all his amazing accomplishments, which you can read on his CV, I could give a talk just about the awards and honors that Bob has received. But I'll just tell you a story from my time when I was a postdoc in his group. So every week we would have a seminar, kind of like this one, where there would be a group of people, students, faculty gathered together, and there would be a speaker. And we had a rule that the first few questions had to be asked by a student. Sometimes, though, the students were kind of shy and hesitant. And so Bob would, wait 2 or 3 minutes, and then eventually he would raise his hand and say, "Aren't we all students here?" And go ahead and ask his question. So remember, it's learning is a lifelong journey, and with the right attitude, we can all be students. So I'll let the speaker actually tell you about topic.
Boris, thank you for the kind introduction. I thank the leaders of the Optica and SPIE student chapters for the invitation to come and be with you today. And especially, I thank all of you for coming to hear my talk. Think how sad and disappointing it would be to talk to an entirely empty room. So thank you for coming. I was told that we are on U of T time. Some of my students who come from a very different tradition, I'll tell you later if you ask, say that you don't know you're supposed to show up 10 minutes early for any meeting, and you sit there with your hands folded on the desk. That is the way you send the message that you want to send. Okay, so it depends on what message you want to send. So this is not the announced title of the talk. It's the same talk. I just switched the titles around so that my CV doesn't look as if I am giving the same talk half a dozen times in a row. So this is the talk that I had committed to give. I post the visuals of all of my seminars on my website. So please feel free. You don't have to write it down. boydnlo.ca. It's something that is easy to remember. Easy even for me to remember that is my website. This used to work. I really want to stand there. Anybody who feels confident to do this, if I move my laptop to right here, I want to stand there. Oh, I have to click on it. I have to click on it. That's it. Thank you. It's so embarrassing. Your IT person just told me that 3 minutes ago. Yeah, that you have to click on it. Okay, so the theme of the talk, no matter what the title is quantum sensing and quantum imaging. Quantum sensing refers to the use of quantum methods to increase the sensitivity of optical measurements. Makes sense. One is often interested in increasing the sensitivity to beyond what is called the standard quantum limit. This is a very strange name because the quantum limit is not a quantum limit. It's the limiting sensitivity that's attainable using classical methods only. Now, one is sometimes interested in achieving the seemingly best possible sensitivity using quantum methods, which is called the Heisenberg limit. This name is also very strange. Delta P, delta X. So if you have no knowledge of delta X, it means that delta P can be 0. So the Heisenberg limit is absolutely perfect measurements. The people who invented quantum information are smart people. Can you imagine if dumb people had tried to come up with the terminology to describe these concepts? Okay, that's what the words mean. People have come to take it differently. I forgot to modify the talk. The standard quantum limit is said when the signal to noise ratio scales like 1 over the square root of the number of photons in the measurement. The Heisenberg limit scales like 1 over the number of photons in the measurement. I guess the number of photons in a given quantum state. Okay, so now quantum. Okay, now that I've bashed quantum sensing, the terminology, a specific example of quantum sensing is quantum imaging, and most of my talk today will deal with quantum imaging. Maybe you have to click. So who knows what happened? Okay, what is quantum imaging? The goal of quantum imaging is to produce better images using quantum methods. Now, everybody in this room might have a different attitude of what it means to make a better image. You might say, oh, it's better because I'll use a smaller number of photons, or I want better spatial resolution, or I want better signal to noise ratio. So all these are legitimate. It depends on the application you have in mind. But these are examples of what quantum imaging can do for you. You can also say that quantum imaging is research that seeks to exploit the quantum properties of the transverse structure of light fields. So as you probably know, over the past 5 to 10 years, there's been enormous interest in structured light, and laboratory methods have been developed to precisely control the transverse structure of a light beam. We have Bessel beams, we have Laguerre-Gauss beams, we have beams that carry orbital angular momentum. We can impress quantum properties on any of these structured beams. So this is one of the underlying technologies that helps us to implement research in quantum imaging. Okay, so here's the outline of the talk that I want to give today. First, introduction to quantum imaging, quantum microscopy for biomedicine, imaging through strongly scattering media, and finally, interaction-free ghost imaging. If you don't know what those words mean, don't worry, you will by the end of the talk. Okay, so introduction to quantum imaging. So maybe the primary resource in optical approaches to quantum information, including quantum imaging, is the generation of entangled photons. You probably know this already. How do you get entangled photons? Standard way of doing it is that a laser beam excites a nonlinear crystal, second order nonlinear crystal. Some fraction of the laser photons split into daughter photons. I'll call this the pump photon, this the signal photon, this the idler photon. Why signal and idler? It's historical. And it's best not to think too hard about why we want to call them signal. Well, the signal is the one you want. And the idler is like a bum who doesn't serve any useful purpose in life. The only purpose the idler serves is to make sure that energy really is conserved. So if you want an explanation for why we call it that, I think that's about as good as we're going to do. Now, these photons are said to be entangled. They can be entangled even simultaneously in a number of degrees of freedom. Polarization, time and energy, position and transverse momentum, angular position, and orbital angular momentum. I just remark that this is the terminology that people use. B, C, and D talk about quantum conjugate variables, but we talk only about polarization. We don't talk about polarization and something because it's not clear what the conjugate variable would be there. You don't have to stop and explain it to me. I do understand. It's a semantic issue that I'm raising here. It's just very strange that for polarization, we express the thought differently. Now, let me give an example of what it means to be entangled. Let's consider the case of time and energy entanglement. So we assume we know our pump frequency. If you measure the signal, the frequency of the signal photon, you can immediately predict the energy of the idler photon. That's only common sense. But if you measure the instant of time at which the signal photon is created, you'll find that the idler photon is created at exactly that same moment of time. Well, to within the pulse length of the pump laser. That is sort of the essence of entanglement. You can make a measurement in 2 different degrees of freedom, and you can make perfect measurements in each of these degrees of freedom. Now, what if you measure the moment of time, instant of time, where the signal photon is created, and then you try to measure the energy of the idler photon? You find that the idler photon does not have a well-defined energy. The fact that you have measured the time at which this photon was emitted prevents you from measuring the energy of this photon with high accuracy. Okay, there's another resource that we often use in optical quantum information, and that's squeezed light generation. Editorial comment: I don't think that, with a few shining counterexamples, I'm not sure that the world has utilized squeezing as often as we should. I think it's a resource that has been underutilized. Of course, I'm going to try to change that, but that's a different thought. So how do you create squeezed light? Well, you take your second order crystal, optionally you place it in an optical cavity, you pump it with a laser beam that we call the pump frequency 2 omega, and occasionally a pump photon decays into a signal and idler photon. These 2 photons constitute squeezed light. Let me explain what is meant by squeezing. We often describe the quantum state of the electric field is a quantum property. As such, it's a fluctuating quantity. So without doing some special method, you find that the real part of E and the imaginary part of E are fluctuating quantities, and they fluctuate over a range which is within this property here called the uncertainty ellipse. Now, this nonlinear process here can figuratively squeeze this circle into this ellipse. The area remains constant, as it turns out, but you can squeeze it. Why would you want to do that? Well, you have decreased fluctuations in this quadrature. So if you measure the electric field using homodyne detection or heterodyne detection, you will get less noise than you would if you made a standard measurement of the electric field. You can beat the standard quantum limit by making a homodyne detection once you've done this. Now, note that entanglement and squeezing share a common origin. In both cases, in fact, my entire talk, I'm going to say, take a nonlinear crystal and shine a laser beam at it. So both of them involve this process of parametric down conversion. So note that nonlinear optics was required to transform classical light into quantum light. I believe that this is a general property, that you need nonlinear optics to turn classical light into quantum light. There is no linear transformation that can turn classical light into quantum light because, well, you need nonlinear optics. You want to think mathematically, you need to mix A with A dagger. As long as you're doing nonlinear optics only with A, or as long as you're doing linear optics, there's no way you can mix the two of them together. Okay, let me tell you about this. It's not quantum imaging, but it's a beautiful demonstration of quantum technologies in work. And this is an idea of the group of David Klitschko in, I think it's fair to say, the Soviet Union. It was still the Soviet Union. Klitschko and Leonard Mandel are sort of my heroes of the field of quantum optics and quantum information. One in Russia, one in the US. They sort of created this field. So what is Klitschko's method? Let's say you have a photodetector and you want to know its quantum efficiency. So what do? The naive thing to do is you get on the telephone, you call the National Bureau of Standards in the US, say, I want a calibrated source. You get the calibrated source that tells you how many photons per second are leaving it. You shine it on the detector and you count how many clicks you get. But there's a much simpler way that Klitschko had pioneered. You do parametric down conversion. Idea is that every time there's a photon here, there's exactly one photon here. You let this photon fall onto any detector. It doesn't even need to be a very good one. But for every time that this detector clicks, you ask what fraction of the time does this detector click? And that fraction is the quantum efficiency for this detector here. So it's so nice, I wish I had thought of it. Which in a sense is sort of the highest compliment you can give another scientist, is to say, I wish that I had done it. Regrettably, he's not alive to hear my compliment. Okay, precision measurements. So this is an example of actually making use of squeezed light. This is Jeff Kimball's work. I should say there was Dick Slusher was the first person to generate squeezed light, but this is the earliest paper I know of that used squeezed light to do a precision measurement. Oh, and let's not talk our way through this diagram here. He wants to measure the transmission spectrum of some atomic gas, and he has a chopper to do lock-in detection. When he does not do squeezing, when the light is turned off, the noise level is down here at 0 dB. But when he makes use of squeezed light falling on the detector, you see that the noise level is like 3.5 dB below the standard quantum limit. So this is the idea. It's he reduces the noise, you can make a more accurate measurement. Generation of twin beams. I'm just doing a rapid overview of what people have done in the past to make use of quantum states of light. There's the generation of twin beams. This was the work of I forgot the clerk, Claude Fabre in Paris. Same picture. You send a laser beam onto a nonlinear crystal, you create two beams of light. If according to this diagram here, you know that any fluctuations in this beam will be mirrored in this beam. So when you get more photons than average in this beam, you will get fewer photons than average in this beam here. So even though each beam separately shows intensity fluctuations, there are no fluctuations in the intensity difference. And once again, okay, I do have his name. He's my friend. I would have felt bad if his name didn't appear. So just doing a spectroscopic measurement, in this case, measuring the absorption of a beam of light going through a potassium cell. When you do it with a laser beam, this is the result you get. When you do it with the twin beams, this is the result you get. If you look very carefully and if you feel very benign at this moment, you'll say, yeah, of course, this is a better measurement than this one here. The fluctuations are smaller. You can make a more accurate measurement. Well, how accurately can you tell where the peak is the question. And if you have less fluctuations, you can more readily tell where the peak is. I think there's also a takeaway message here. Quantum technology helps, but not that much. I mean, it's maybe a factor of 2 or the square root of 2, depending on the exact geometry that you are studying. Now, a factor of 2 is enormous if you're at the shot noise limit. I mean, if you are at what you thought was the fundamental limit of how accurate you could make a measurement, and someone says, I can do a factor of 2 better, you're not going to turn that down. But keep in mind, it's only a factor of 2. And I think the message is do your classical optical engineering right. You want to be at the limit of how well you can do using classical methods, and then you get that extra factor of 2. So, again, just so that all my friends see their names up there, I said early work. So this is confined to old people. So if you don't see your name there, you can be very, very happy. Kolobov and Prem Kumar were the first people to note that we're the first person to note that you can do microscopy with higher resolution. In this case, the ability to detect the, not spatial resolution, but the resolution of how much phase change you can get. You use squeezed light. And you use multi-transverse mode squeezed light. This was a theoretical study. It wasn't until a few years later that this was actually implemented. And quantum lithography, this is a great idea. I just love it. I say that there's been no practical implementation to date. Since I am the author of the work, I tell you that this was not practical. But it's a proof, it was one of the early proof of concepts showing that this method works. So what is the idea? You take a laser beam, you excite a nonlinear crystal, you create signal and idler photons, and make sure that these are indistinguishable photons. So you adjust the phase matching just right. Then these 2 photons meet at a beam splitter. If you go through the quantum theory of the beam splitter, you find that half the time both photons emerge from the upper port, half the time they both emerge from the lower port, but you never get 1 photon here and 1 photon here. The photons then fall onto a holographic plate, This is a holographic plate that is designed to be two-photon sensitive. It is not your standard holographic plate. It's a two-photon holographic plate. I think all holographic plates will respond to 2 photons if you're below the wavelength threshold for 1 photon excitation. But okay, so you write an interference pattern. This interference pattern is it's a quantum interference pattern. The probability amplitude of both photons coming from the upper port interferes with the probability amplitude of both photons coming through the lower port. And you get this structure here, and the fringe density is twice as large as the density for a standard interference pattern, just using coherent light in each of these ports. Well, and here was a demonstration in my laboratory. This is data. This is the classical interference pattern. Here's the quantum interference pattern, and you can see that the density is twice as large. So the original idea of John Dowling was that this could be used in the context of photolithography to write even smaller features than we have right now. You tell me the shortest wavelength you have, and John Dowling says, I can buy you another factor of 2. Now, the trouble with this approach is that I worked with John on this. We never got beyond writing sinusoidal patterns. Now, you need to write complicated things to build an integrated circuit, but we'd never found an even plausible practical way to use this method to write arbitrary patterns. Okay, now let's move on to quantum microscopy for biomedicine. So this is one of my first forays into biophotonics. I put it here more toward the beginning of the talk. So something I really wanted to say, I didn't want to save to the end when I was running out of time. Okay, so first of all, what's the motivation for our particular work? Well, many biological samples require low illumination intensity, long wavelengths, and the use of phase imaging. Why? Well, because biological materials tend to suffer damage when they are exposed to intense light, especially light at short wavelengths. I tend to get sunburned. So from personal experience, any redheads in there? So I can tell you from personal experience that short wavelength light, even from the sun, which is a long ways away, it can cause damage to biological materials. Well, you just go to long wavelengths, but then you lose spatial resolution because of the Abbe criterion. You can just use a very low intensity, but then you lose signal to noise ratio. And also, many biological materials, especially cellular materials, do not offer very much intensity contrast, but they do offer a lot of phase contrast. So you want to build a phase microscope to, a phase quantum microscope gets around all these problems. So okay, here is our microscope, which works. First, let me tell you, it works. So if you're tempted not to pay attention, this works. And for a crowd of people, the laser 405 nanometers. You wouldn't believe how many 405 nanometers I saw afterwards. So that much you're familiar with. That's what you rotate the polarization, send it off a mirror, and send it through a BBO crystal. This is a second order nonlinear optical crystal. You create a signal Idler pair traveling in a forward direction. You put your object here, which could actually be a object on a microscope slide, or for quantitative work, you write the object, a synthetic object, on a spatial light modulator. So you put a phase object here and a mirror behind it that sends this light back. Now, you also took the pump beam that's already gone through the BBO. You split it off here, you rotate the polarization, and you send it back. You get a second signal Idler photon created on the second pass going in this direction here. So now you have a signal Idler pair that does not contain the image information, and a signal Idler pair that does contain it, and they interfere with one another. So you get the interference pattern, the two photon interference pattern between the reference wave and a image bearing wave, and you let this interference pattern fall onto a CCD camera, and then you play standard tricks. You take 4 images with different phase shifts. Phase shifting, you implement phase shifting holography. And then there are standard algorithms by which you can back out the structure of the material. I guess I should mention this is primarily a Rochester project. It is done in collaboration with the Pacific Northwest National Laboratory, which is part of the Department of Energy in the US. Oh, and just for comparison, we can very simply turn our quantum microscope into a classical microscope by, well, removing the nonlinear crystal. We make sure that we have the same numerical aperture in both cases, because we want to show that this microscope gives better spatial resolution than this microscope here. So we don't need to dwell on this point here. Okay, here is a comparison. So my students chose the object to be my eyeglasses. For as long as anybody can remember, I have worn perfectly round eyeglasses. Why? Well, round eyeglasses are the prototypical example of eyeglasses. This is a monument in Ueno Park in downtown Tokyo. It's a monument in honor of the spectacles. My wife said, they're your eyeglasses. I said, what do you mean? I looked around. No, they're still here. What do you mean? I said, no, look at that monument. Look. He said, hey, gotta take a picture of that. Okay, so anyway, so first of all, here's the object. This is the phase distribution of the object written onto the spatial light modulator. Well, these are the actual pictures, first of all. These are the actual pictures of the object, the classical image, the quantum image. Quantum image seems noisier, but it's sharper too. So take a cut through the nose piece eyeglasses. We press it power phase shift using a spatial light modulator. The classical image looks like this. The quantum image looks like this. You see that the signal is twice as large. The noise is about the same, but the signal is twice as large. So we have an signal to noise ratio. And if you look carefully, you can see that this image here is sharper in the quantum image than is in the classical image. So the signal is twice as large in the quantum setup and 1.7 times sharper in the quantum image. And we had a superb team of people working on this project, didn't we? Thank you, Boris. Okay, and just so we can quantitatively compare the spatial resolution. We have the standard trick of some bar charts, and let's see, experiment simulation, experiment when they are this far apart. The classical microscope cannot resolve the separation, but the quantum microscope can. So this really does work. Did we establish a quantum advantage? Maybe, maybe not. This is right at the diffraction limit. So I'm not sure that the classical image really was at the quantum limit. Certainly the quantum did better than the classical, but the classical, was it at the quantum limit or not? I said earlier, you have to do your optical engineering correctly. You have to do your optical engineering correctly. We are designing our own microscope objective. The Rochester, home of Kodak. So at Rochester, there's still a large contingent of people who know how to design microscope objectives, and we got their help. Why didn't we just go to Thor Labs and buy their most expensive objective? Because our criteria is different from theirs. It's crucial to us to have as small a loss as possible. This shows how the signal to noise ratio plotted against the number of photons per resolution element depends upon the nature of the illumination. This is the classical limit down here. This is the quantum limit up here. You see that the quantum is much better. It gives you a much better signal to noise ratio. But if you have even 20% loss, the prediction for the signal to noise ratio drops markedly in going from here to here. So if you look at the specs for commercial objectives, you will be surprised by how they are in terms of total transmission, maybe 50%. Why? Because people want them to be achromatic over a very large spectral range, and they want them corrected for spherical and chroma. But it's especially removing chromatic aberrations that requires these objectives to have maybe 10 lenses in them, 10 refracting elements. And we got by here with 4 elements. Okay, so we're trying to build this right now. We're trying to find some altruistic fabrication company who will build this for us. You say, oh, if you build it for us, we will give you the rights to market it. But there's nobody in the world except you who would want to buy it. Okay, so that's where we are right now. And we actually do have some laboratory results using the quantum phase microscope. It's actually a slightly different configuration. It's a quantum Numarsky microscope, but these are living yeast cells, and we are just about, we have like 1 micron spatial resolution, maybe slightly better than 1 micron spatial resolution. So this was crucial to our sponsors. They said, it's not good enough that you did this with test charts. we want you to do this with some biological material, even living biological material. So we hope they're happy. Well, they are happy. We just, the process is financially limited. We just found out we were refunded. I mean, within the past week, the money has arrived. Okay, imaging through a strongly scattering material. This is not really a quantum method, but my own feeling is I don't want to be that hung up on what is quantum and what isn't. There are precise definitions that some people have advanced for what constitutes a quantum state of light. My own feeling is that if it works, it works. Who cares? Okay, so how do you image through a strongly scattering material? Well, first of all, it works. I'll get to that in a minute. So if you have an object and you make an image of the object, and the light passes from you to the detector through free space, it just goes through. But if you have a highly scattering medium, the photon might scatter several times before it comes out, and it just takes longer. It takes longer to go through the scattering material that does through free space. So what you want to do is you want to get a very, very fast shutter that you look only at the first arriving photons. Because the first arriving photons contain the information. So we need a material with a strong, fast, nonlinear optical response to construct a time gate or a shutter. And we use indium tin oxide. It has a very large nonlinear response at the epsilon near zero wavelength. And that is a story of its own. So what we came to realize is that there's this enormous excitement now about ENZ materials. If you can find a material in which the dielectric permittivity vanishes at a certain wavelength, then everything you thought you understood about optics has to be rethought. If epsilon vanishes, both real and imaginary parts, that vanishes, then the speed of the phase velocity of light becomes infinite. That means that there's no time delay in going from point A to point. So everything is different. But what we realized is that there's a fundamental relationship between chi3 and N2. And in an epsilon near zero material, N2 is, did I shoot here? Yeah, well, here it is. But what we realized is that there is a relationship between N2 and chi3, and this depends upon the refractive index times the real part of the refractive index. Just assuming that epsilon is real, that means that N2 scales like 1 over epsilon. If epsilon vanishes, you get a huge enhancement of the nonlinear response. And here's some data. We find that N2 is approximately 300,000 times larger than that of silica glass. We chose silica glass not just so that we can make a very extravagant plane, but because many people use silica glass as a calibration standard. I mean, anybody, anywhere can get silica glass. So people say that they quote the nonlinear response to their material in comparison to that of silica glass. Okay, so back to here, we have these shutters. We took a bar chart with, well, first with no scattering. This is the control. We just take a picture of it, and this is the bar chart. We have weak scattering here. This was a ground glass plate. Here we have 3 ground plates. Here there's the background, but you can still see it. Here the background is so strong you can't see it at all. Now, Here's the time-dated image, and in all three cases, you can see it. So if you say, isn't this deja vu? Didn't Alfano do this in 1991? Yeah, but since 1991, people have come back to this problem saying, oh, but we're using a different method. Our method is better than that of Alfano. So I'm telling you, we did it differently, and our method is better than that of Alfano. So you don't want to see this. Sure. We are using some frequency four-way mixing. So here's the interaction. We have a gate pulse that tells the shutter when to open. Here's the signal pulse that we want to see. The gate pulse is timed so that the gate opens up for a short period of time, 100 femtoseconds, say, when the signal photon has arrived here. Now, other people have just looked in the forward direction. Here's the camera looking into a strong laser beam. Sounds like not a good idea. We're doing four-wave mixing, so the phase matching condition tells us that the image is transferred to this beam here, which is emitted at a different direction. And this is the phase matching diagram showing the direction at which the light is emitted. So indium tin oxide has a huge nonlinearity. Because of that, we can use a very, very thin sample of indium tin oxide. Because the material is so thin, phase matching is automatically satisfied. Delta KLO2 and all that. So it's automatically satisfied. So we get all these output beams. But what we want is the some frequency four-wave mixing. So it's this output beam that we want. We don't want to look at the other beams here. So this is how we did it. And this is why we think that our approach has a lot of promise to it. Now, the obvious limitation, I'll say it so you don't have to, is that the field of view is too small. By the way, this is at the diffraction limit. This is at the diffraction limit. So we don't need to try to improve the resolution. What we need to do is to increase the field of view so that this becomes plausibly useful. And that is the next step. That is the next step in our progress down this pathway. Okay, this is the last topic. I assume we end on U of T, Tom? It's only fair, isn't it? Okay. But this is my last topic, so this will go quick. We're doing interaction-free ghost imaging. So first of all, what is ghost imaging and what is interaction-free imaging? So first of all, what is ghost imaging? This was the idea of John Dowling. No, it wasn't. It was the other project. This is the idea of Yanhua Shi working with is it Dmitry Strekalov? So here's the idea. It all starts the same way. A laser beam excites a nonlinear crystal. You generate an entangled photon pair. They only have to be correlated. They don't really have to be entangled. One of them falls onto the object you want to image. Maybe the photon gets transmitted. If the photon falls upon a dark place on the object, it won't be transmitted. The other photon falls onto a photodetector array, and you look in coincidence. When you accept the data from the photodetector array only when it's accompanied by a click from this detector here. So this is called ghost imaging, not my name. because the image is formed by photons that actually never physically interacted with the object you want to image. This has obvious applicability, potential applicability to remote sensing. There was an enormous discussion in the early days about whether this is a purely quantum mechanical process. Common sense says it's not. I said entangled photons, but they don't have to be entangled. They just have to be correlated. Luigi Lugiato and his co-workers wrote this paper that really addressed the issue from a fairly fundamental point of view. They say that you don't need quantum states of light to do ghost imaging. You do want to do quantum ghost imaging. If you want to do quantum ghost imaging, the way you're sure that you're doing it correctly is to simultaneously have spatial entanglement in the near and in the far field. So when a leading theorist says that, what do? You do the experiment. Okay, so here was the experiment. We just had a slit pattern, and with the quantum source, we resolve the slit pattern in both the near and the far field. But with the classical source, you can resolve it only in one of the fields. In this case here, we had it set up so that we had good resolution in the far field and no resolution in the near field. So ghost imaging, isn't that cute? Is it useful? A lot of people have questioned why this is this useful? And we think we have one example where it's useful to do wavelength shifted ghost imaging. Who ever said that the wavelength of the light that interrogates the object has to be the same as the wavelength of the light that falls onto your detector array? And detectors have a certain wavelength range where they work the best. And maybe you want to know what the object looks like in the infrared. So we took an object, a stencil, and we wrapped paper around it so that visible light wouldn't get through, but the infrared light got through. We did the ghost imaging, and we found that we were able to see in visible light what the object looks like in the infrared. Okay, now let's get back to some fundamental issues. What constitutes a quantum measurement? And some respectable physicists have worked on this problem. So what constitutes a quantum measurement? Let's say you have a single photon falling onto a beam splitter, and this detector clicks. So you've made a measurement that tells you that you had a photon that was transmitted by the beam splitter. Let's say the detector does not click, then you know that the photon must be here. Yes, but how do you know that you have a single photon here? So the whole issue here is that how in the world do you know for sure that you have a single photon here if you don't do a measurement to determine what it is? This is just background. Just keep that in mind. I think it motivates what's coming next. So this is quantum imaging by interaction-free measurements. This was an idea put forth by Elitzer and Lev Weidman. in 1993. Here's the idea. You set up a Mach center interferometer. You can either put an object inside the beam block inside the interferometer or not. Let's say that there's no object here. You adjust the path lengths so that a single photon will always exit through this port and make this detector click. You never get a click here. Now, let's say you put a beam block here. What you discover is that 25% of the time you get a click here. Your first thought is, yeah, that's how things work. Second thought is, gee, you only have one photon. The photon has to be here to know that the object is there, but the photon has to be here for this detector to go click. So it's a bit of a paradox. I think a lot of people say it's a paradox only if you think wrong about it, but it's a paradox. It's a very strange effect. So Andy White, Paul Kwiat, and their co-workers decided to do an imaging version of this experiment. So here's the output of here is their vitamin interferometer, which I will call it. They put a microscope in one arm of the interferometer. The object is a thin wire. They translate the wire through the focal region here, and they plot out the fraction of the time that the other detector clicks, and here are the results from one detector and from the complement of the other detector. But you see they're able to measure out the cross-sectional transmittance of the wire using photons that did not hit the wire. So it's still a little bit mind-boggling. Okay, so that led Ibrahim Karimi and me to think of, hey, here's a variation that we can do. Let's combine ghost imaging with interaction-free imaging. One second. How did that happen? This is called an interaction-free measurement. Maybe that's not the right name. Clearly there's an interaction. It's maybe not the interaction you were thinking of, but there was certainly an interaction going on here. I bet you never knew you could switch the mode of this by using just this clicker. View. Okay, so here was our idea. Build a source of entangled photons. One photon falls onto a photodetector array. The other one falls onto a Weidmann interferometer. You have a small opaque object, crucially small. It is smaller than the diameter of the laser beam inside the interferometer. And the question is, well, without the object, only this detector goes click. You put the object here, and 25% of the time, this detector, maximum 25% of the time, this detector goes click. If the detector clicks, it tells you that this photon was localized to a region smaller than the total diameter of laser beam. It was localized to the size of a small object. Question then is the distribution on this photodetector array similarly decreased in size. If this were a real measure, these are entangled photons. If this is a real measurement, then in coincidence, this photon would have the same spatial distribution as that photon. But this isn't really a real measurement. So you can question whether it will, whether the spot size on the array will decrease. The question is, does an interaction-free measurement constitute a real measurement? Or does it lead to the collapse of the wave function of its entangled partner? Or perhaps more accurately, does the entire two-photon wave function collapse, or does only this part of the wave function collapse? And if you don't like the concept of the collapse of the wave function, just bear with me. Here are the laboratory results of a straight wire. So the singles counts looks like this. The coincidence counts, well, there's a background, but the wire shows up as a very thin object. So note that the interaction-free ghost image is about 5 times narrower than the full spot size on the intensified CCD camera. This result shows that interaction-free measurements lead to wave function collapse, just like standard measurements. So again, why would anybody waste their time doing this measurement? Some theorists said, you don't have to do the experiment. I know what the answer is going to be. And I said, Professor blankety blank from Toronto, I know that whatever answer I get in the laboratory, you will find a theory that matches it. So don't tell me that it's obvious what the answer is going to be. He was right, but that's what I said to him. Okay, why is this useful? Interaction-free imaging allows us to see what something looks like in the dark. Strange concept, isn't it? I mean, no photons were absorbed by the object. So the object is in the dark, but you know what it looks like. How often in life do you know what something looks like in the dark? This could be extremely useful in biophysics. What does the retina of the eye look like in the dark? What about the green alga, who I can't pronounce? It's commonly used in the study of photosynthesis. So how does this object act when no light hits upon it? Was this experiment worth doing? So again, some people say we could have done the experiment theoretically. My response is that physics is an experimental science. The theoretical model has to explain the results of the experiment, not vice versa. And even in their original paper, Elitzer and Weidman say, assuming that detectors cause the collapse of the quantum state. And the emphasis is mine, but say, let's assume that it does. So they were not at all certain either what the results of this experiment would be. This summary I should have removed because I've said everything at least twice already. So time is up. I forgot, there actually is another section of the talk which I've never had a chance to finish. But this is my summary slide, then. This is my summary slide. Here are 4 configurations of quantum imaging that have been popular recently. There's the ghost imaging of Yanhua Shi. There's the imaging with undetected photons that we didn't have time to talk about. This is Anton Zayon's work. There's the interaction-free imaging, and there's the interaction-free ghost imaging. And no matter how stupid the joke, the more I like it. So whenever I hear people say quantum imaging, I think they're saying quantum imaging. So this is Sid Caesar, this is Imogene Coca. They were television stars in the early 1950s. So I can imagine a whole series of PhDs studying the quantum nature of imaging. So thank you very much. I'm done. So I guess I'm be happy to answer questions. Or I'll sing to you.
SLM similar target to. So I mentioned, I remember that this is one type saying that the actual photon flux per square micrometer is around 60. And I'm wondering if the experiment, that kind of advantage can be scaled up if you're using a higher flux rate.
I'm not sure. Which experiment of mine are we talking about? Or are you asking a conceptual question?
No, experiment where you have a spatial light modulator. Oh, your eyeglass.
Yeah.
So I remember that.
The flux level. I said that, right? Did I? That was on the slide?
Yes.
Okay. So I didn't say it out loud. I know that. So let me go back and try to. I know the slide. Again, what slide am I looking for? Eyeglasses. Oh, this, yeah, we're almost there. This one.
Yeah.
Okay, the photon flux was 40 photons per second per micron squared, which is a pretty low flux, right?
Yeah, so I'm wondering if this kind of point advantage can persist if you increase the flux to very high level.
Good question. Oh, well, the safe answer is I don't know. Showing the quantum advantage would be very difficult if you have so much signal to noise ratio in the classical measurement that you couldn't see the difference. But I will think about your question. I mean, it's a perfect conceptual question of what would happen if the intensities were much larger. Well, one answer is you don't need quantum methods if it's much larger, but that's not a good answer, because no matter how good your signal to noise ratio is, you would always like it to be better. So thank you so much. I will think about that.
Much simpler question. Your classical image, why do you have these rings around the glasses that didn't exist in the object? These kind of lines that you see.
Oh, in the classical. I will find out. I think it's phase wrapping. I suspect it's phase. Boris, wait. Boris, why do we have those rings?
I mean, they look like.
They do look like diffraction frames.
Right.
Yeah.
So the classical image is taken here in play,
Mm-hmm.
whereas the angle photon spatially full. They wash out. Okay.
So another good question. I don't know the answer.
In the interaction rate experiment, the example that you gave bacteria,
Mhm.
and you're saying that you're never trapped. The interaction rate experiment always messes with my head, but
Yeah.
in my eyes, it still would attract the like percent of the
Let me,
Maybe the first one,
let me-
those
let me-
interact, you can say that, but then the next photon, you'd have to have some sort of time difference in between, the individual.
which one do you want to look at?
Just any interaction for the experiment.
Okay. Let's go here.
We replace the object by this bacteria. right,
Yeah.
that You were saying, there is still like some interaction that could turn the time to the light goes upwards, right?
Yep.
So then that ruins the entire promise experiment of interaction with the bacteria, no?
Let me answer. The trick, professors, no. I will answer the question I wish you would ask, because I know the answer to it. And then I'll give you a chance. From a practical point of view, 1/4 of the time, the light will fall on the biological sample, and that will tend to degrade the biological sample. So from a practical point of view, is this practical? You'd want an ensemble of identical objects. And when the photon hits the object, then you take that object away, you replace it by an identical one. So that is the response to sort of an obvious criticism of this method. Maybe that's what you were getting at.
Yeah.
Mhm.
Still doesn't seem perfect.
Mhm.
Okay.
Can't hear. Yes.
What exactly is?
Let's go look. Let's go look. Ooh. This looks different than that. That's your comment. I forget. Yeah, it's we know why. I don't know why. It's something to do with how they set up the imaging system. By the way, this paper has not been accepted for publication. Maybe for reasons such as the one you just mentioned. We're still working on this. We are still working on this. I said we want to get a bigger field of view, so there's a bunch of tricks we are implementing to get the field of view larger. Thank you. Oh. Yep. Two, you said?
Maybe more. More. Yes.
Okay.
So you mentioned earlier that in quantum advantage, you have a factor of 2 or square root of the base.
Yes.
Half 1.5 dB. But here you see like much more than that. The difference between the S and R.
Right. There's a lot. There are times in life where you believe you're a graduate student. It's a log scale. So here, 33,000. It's a different setup, I guess. In many cases, you get a very modest enhancement. I showed you published data from other groups in which the enhancement was barely perceptible. This is a plot of equations taken from this paper here. The paper seemed to make sense to us.
Use my chair's right.
You know, the answer.
Comment.
Yeah, thank you, thank you, thank you.
Here is the yellow.
Mhm.
Right? The orange curve is indicates when there's no law.
Right.
It's basically the amount of benefit you can get from any kind of quantum scheme is always limited basically by the loss. So if you look at the curve, the yellow curve is 5 times higher than the blue one. That's the 80%, 20%, 1 of 20%. That's kind of the general rule of thumb. And most systems have like 50% loss. They get back.
And the video, that one is more than 0.55. It's like 10 times.
Sure.
10 times 10 dB.
Yeah, but basically the point is that if it was 50% loss, it would be low. If it was 10% loss, it would be 5. So the loss limits you to a constant again.
Wait. So my question is theoretically, it's not right? Or yeah, that's.
We're experimentalists. All right.
Well, the wave like this thing.
Yes?
What wave like?
Oh, so I just really skipped over that very quickly because I didn't think anybody would care. And because it was sort of peripheral to the going the wrong way, right? No, I'm going the wrong. I'm sorry, what was the question?
So in the wavelength shifting.
Wavelength shifting. Okay, sorry. Here. Okay. The question is, what were the wavelengths? So we had a 355 nanometer pump laser, non-degenerate down conversion. One photon was at 1550 nanometers, and the other was at 450 nanometers. So the 1550, this is just a conceptual experiment. We said a lot of people want to know what things look like at 1550 nanometers. Because that's a standard telecom wavelength. And we had this laser, and then the other one turned out at 450, which is a very good wavelength. Still, it's a good wavelength for silicon detectors.
So bumps. No, that actually wasn't my question. My question was, will you always be limited by the long wavelength in terms of resolution?
Oh. It's the wavelength that hits the object that determines the resolution.
What if you could?
By the way, I had to show that anyway. Before answering your question, yeah, I had to set the stage for it. So you go through the analysis. It's not always simple to go through the analysis. But luckily, the analysis turns out the way it has to turn out from a information theoretical point of view. It's the wavelength that falls onto the sample that determines the best possible resolution. Of course, you can always do worse than the best possible resolution, but at some time, a very, very fraudulent member of this community was saying that you could interrogate the object with the long wavelength and get the resolution as if you were using a short wavelength. And to the best of my knowledge, that is simply wrong. And that rumor did not persist for very long. People said that, I think when you say something stupid in public, one way or the other, people tell you otherwise.
I'm gonna ask this question about what constitutes a quantum measurement. I'm gonna make a statement and see if you agree with it or not.
Okay,
If the experiment involves entanglement, your damn sure is quantum. Anything besides that, the jury is out. That's the first one. Second one, don't forget to give me my help back.
yeah, well, no, I won't.
So what do you think about the first statement? If it is entanglement,
If-
because that doesn't have a counterpart in class.
Let's get that slide up here, because I think the answer to the question depends very precisely on what the question is. Well, you should say that's always true, but some questions lend themselves to fuzzy answers. This one doesn't. So again, so I was not necessarily talking about entanglement, but I think you're saying maybe you have entangled source here, and that creates a signal in an idler photon, and you herald the presence of this photon with the other photon? Is that what you were asking?
Well, depends on the entanglement of the two states.
It doesn't.
But that doesn't have a counterpart in class.
This does not. This says, imagine that you have a single photon falling onto a beam splitter. So imagine, there's other ways of getting single photons. In resonance fluorescence, you excite an upper state, it decays, it can emit only a single photon. So I think that was historically one of the first demonstrations of single photons was demonstrated that way. And what was it? It was a measurement of photon anti-bunching. Thermal sources usually give bunched photons, but resonance fluorescence will necessarily give you anti-bunched, because there's no way that you can send two photons simultaneously, because you have to pump the atom back into the upper level before you can get the second photon. So, but now to answer your question, all we're saying is that send a single photon onto a beam splitter, and I didn't say how we get the single photon. Yep. Which slide?
So, concept is, you're saying that, well, if the photon goes straight, that's the photon that we want to measure.
Hmm.
But when you think about imaging, photons are not particles, right?
Yeah.
It's a wave. So we are trying to get the far field diffraction pattern. So then I'm thinking that there could be many paths adding together.
It could be what?
Well, different paths.
Yeah. Yes.
Right, that's because when you.
Yeah, there's different scattering paths.
Right, when you calculate far field diffraction, you have all these different paths and they add.
Mm-hmm.
So classically, if you can think of it that way. So does that mean, that the photons that make this image may not always just take the straight line the shortest. Well, I mean, doesn't necessarily this particular.
Oh.
The other paths that add to it that creates the image. So if you gate at a very specific time, then aren't you blocking out these other paths that form the overall image. the overall
Yes,
image.
yes. That is one of the next steps on this project. I said the next step is a bigger field of view. The other next step is conceptually more tricky. I think it's just what you said, but I've lost my pointer now.
Right here.
Thank you. We are looking at the first arriving photons. We're throwing away everything else. There's a lot of information encoded in these other photons. It's sort of silly to throw them away. We're just decreasing the background. The only thing that this method does is to decrease the background. It does it at the expense of throwing away 99% of the light, which does not sound like a good idea. So what we're just starting to do now, I said this has not even been published yet, but the next step is to try to extract as much information as possible from this scattering pattern. The world knows how to do it, at least in concept. In going through a scattering medium, there are eigenchannels. And there are laboratory ways to determine these channels through the scattering material. So the idea is to determine the eigenchannels, determine the time delay for each of them, take the object, decompose it into these various eigenfunctions, correct each one for the delay time, and put the whole thing back together. Boy, does that not sound easy, but there are enough hints in the literature to make one think that this is not impossible.
I guess my question is, right on the photon, thinking that gets the image.
Say that again louder, please. Yes.
Right, like,
Well, you're throwing away 99% of the light, but there's an image in the 1% that you're keeping. And under certain conditions, the fact that the background is so large is more, eliminating that huge background is more important than extracting the maximum amount of image information from the transmitted field. This is a very crude way of doing it. I mean, it's embarrassingly crude. Why am I using a technique that is this old? Well, because it's the first step along a pathway that I'm trying to take. And the pathway I want to take is just in line with what you're saying. No, it's 80% in line with what you're saying.
Maybe two last questions. Bit of a more general question. You sort of alluded to that epsilon zero gene earlier.
Yes.
I was just wondering if there been any sort of more practical implications of that suggested?
A huge number. A huge number. In fact, I have committed to giving a plenary talk at Meta, the Metamaterials Conference. And what I want, and that's what I want to do, is to outline the various applications. So Alan Wilner and I have worked together on much of this, and other groups as well. But there are now dozens of papers of people who have used this epsilon near zero method to get very high nonlinearities to allow them to do measurements that they could not otherwise have done. At least I hope that's true. Well, I mean, the papers are certainly been published, but let's hope that the papers are not written by artificial intelligence.
In the front.
Yeah,
Might be a bit obvious, but I don't fully get it. In the ghost imaging section, when you first were introducing it, it said that we don't necessarily need entangled photons. We need correlated photons.
right. Correlated in emission direction.
Right. And you said there's set up to showcase that if they are entangled, then we would see the images in both near field and far field.
Well, Lugiato said that.
Yeah.
Lugiato said that.
Well, I don't understand why he said that.
Oh, well, you have to read the paper.
Okay.
He's a theorist. What can I say? He's my friend. It's nothing but common sense that you don't need entanglement. And if you're a theorist, after 4 pages of heavy algebra, you come with that conclusion. And his statement in the abstract was poorly worded. He says he'd used the wrong word. He says you need entanglement in both the near and the far field. He means you need correlations in both the near and the far field to show that you have entanglement. Oh, but it's so easy to criticize somebody on a paper that they wrote 20 years ago that you now finally understand.
Let's thank Professor Bill.